you set the scene, and then I'm literally just going to play student.
We're playing supervisor then.
Don't want to see your spreadsheets. Show me hand calculations.
Don't get up, Mark. I can't see you at this point.
Told you to meet me 15 minutes ago.
Been waiting outside your office. Shame. Okay, so welcome to the third episode of the Design Podcast. We're still calling it Toasting Design. You have yet to stop us. Today, we're just joined by myself, Schekman. Once again, Mr. Boer. And then today, we've also got Mr. Van Aswegen, Mr. Dean Van Aswegen.
Known as Van Aswegen to students.
Why not? So the first, we're just going to start off. You've been sending in some questions already, so we thought we could start in at least answering the first one. And then we're going to shift gears a bit because the main idea we're going to tackle today is how students, or we can be presented with an idea, and in isolation, that idea appears really good, or let's put it this way, it appears okay at the very least. But when you put all these okay ideas together, it's horrific. And then you start asking, or someone starts asking, how could I have failed? How did you give me a mark of 20% when you actually look at the grand scheme, it is horrific. So the first question we're going to be tackling today is from Anonymous, because they all tend to be. How do I know when an assumption is reasonable and not a bad assumption? I mean, what's a bad assumption? Let's put it that way.
Well, if you get to a design that's completely crazy and unreasonable based off your assumption, it's a good clue that it's a bad assumption, although that might be slightly too late.
Yeah, well, I think that's the problem is when do you decide that it is a bad assumption? I think it comes down as well to what level of design you're planning on taking yourself into. You're going detailed design, then assuming a part doesn't exist, or assuming a mass is completely negligible, or that gravity is not going to apply in this particular situation, that's probably no longer allowed.
I think it really comes down to a basic understanding of how much effect this assumption is going to have on your overall system. So if it's going to lead to a 50% error in your performance, then it's probably not an assumption you should be making. But if it's something that's going to make a 5% difference at a high level stage, it's fine to ignore something like that. And as you go to more and more detailed, that percentage threshold gets smaller as you zero in on the perfect design, if there is something like that.
Actually, yeah, I mean, it's actually pretty much dead on, because anytime you come up with an assumption, don't just run ahead. First, rationalize to yourself, what is the effect of this assumption? What is it? I mean, you're going to have to say that in some kind of report or communication at some point. You're going to have to say, I've assumed this. What you should be able to then say is, this will have this effect on my design, or this effect on the system, or this effect on the component, and is that severe enough or not? And if it's not, if it's a 50%, this affects, means I can't use the speed, I can't use my acceleration, I can't use any of the performance aspects because of this assumption, that's a bad assumption. If it is a case of this is likely to result in a 1 or 2% error, that assumption is certainly fine.
Yeah. I mean, if we can think of an example of a car, if you look at the weight of a car battery, for a conventional internal combustion engine vehicle, you can assume the weight of the car battery is negligible on a 2.5 ton vehicle. However, if you're looking at a 2.5 ton electric vehicle, you definitely can't assume that the weight of the battery is negligible. So that's the same assumption being made, but based on the context, one is completely invalid and one is acceptable at a high level.
The other one I see quite often is the assumption that sticking to a two-dimensional analysis is always okay. It's always fine. When you have a short little stubby winged aircraft and you're assuming just 2D analysis over the entire thing, it's perfectly fine, there's not going to be any issues. That's a problem, because you're ignoring the whole three-dimensional flow effects. You're assuming that a vehicle's center of gravity is always dead center in the center of the vehicle. Maybe as your first set of preliminary analysis, fair and fine enough. But taking it any further, that assumption is horribly inaccurate and affects a large number of factors in the design and its performance.
But even with the inadequate assumption, if you understand the effect it has on the design, you can still use it to spec out an initial concept.
Yeah. No,
if
exactly.
You understand that a 2D assumption is going to give me more lift than the real-world 3D case, you know that you're working with a very inflated lift value, so you will adjust your design accordingly, and then you won't have too many adjustments to make when you use more specific assumptions or analysis methods.
No, exactly. Yeah.
I think assumptions are also linked to sort of the understanding of physics. And the one thing which has become apparent with students at the moment, obviously not all of them, is, if you talk to them, how's applied mechanics B going? The students will be able to tell you, oh yeah, the test was about chapter 2 and then chapter 5 and then chapter 7. But I'm not worried about the exam because chapter 9's not in it. But actually, if you're trying to analyze, how a beach buggy goes over a sand dune, the beach buggy doesn't care about the different chapters in a textbook. And the thing is, if you're trying to, if you take second year materials as a prime case, you can't just look at things as a, Young's modulus and view that in isolation.
Yeah.
You've got to sit and think, there's a little bit of thermodynamics here because this is a ship that's trying to navigate through iceberg-infested water, where no Bert Russells are present.
They're always a killer on those ones. Speaking of Bert Russell, we can't forget we've got rules for most of these podcasts.
In our new 20-minute version of
In our new, sure, why not? Let's go into a whole number of sidetracks here.
The poor assumption is that it's going to be 20 minutes.
But you assumed it was still 45, Mr. Schekman. That was an incorrect assumption.
All right, so I'm going to just ignore that and go into my rules. So the rules are, first rule, when talking about a task or talking about what you to do, you don't mention the word design. Second, swearing, try and avoid it if best possible.
Can you let us know what the swear words are?
Say them. That would be one of them. Third rule, obviously, no mentioning of Bert Russell. And then fourth rule is no jumping into concepts. So when you got an idea, you immediately have solutions that you think, this is what I'm going to do. You need to substantiate that before jumping ahead.
Right, so we're just going to role play a fourth year project from a couple of years ago, and I had the privilege to supervise both of these now a little slightly older as students. So now
you're old,
to
Mike.
shut up.
You also know
that's swearing.
He means us.
Yeah,
We're the young ones.
yeah. So that's the project which I've selected.
Okay, so the student's coming to me with a regenerative braking system for trains on the all line from Seshen to Sultana. Sure, what could go wrong with that one? Okay.
Cool. So as we said, it's a fourth year project, and fourth year projects can go wrong where there are incorrect assumptions, so what's going to happen is I'm going to talk to the supervisors about my sort of plan and sort of explain what this design is. They're going to give me feedback on that as we would do at second, third, and fourth year level, and then I'm going to let them know what exactly the student did and how badly wrong it actually went.
Considering that when we were told this information, you're not told the entire design up front at every meeting. You're told, right, this week I've done this week I've done this, or I'm now at this point. You hear it in snippets and small bits.
And it becomes intermingled with the 20 other design projects that you've heard about over the last 5 minutes.
20 fourth year projects, the whole third year thing, etc.
Exactly.
It gets busy.
Okay, so meeting number 1.
All right, so students have to formulate exactly what the problem is.
Sure.
All right, so South Africa exports a hell of a lot of iron ore, and they do that through mines in the Northern Cape, and there's a dedicated railroad which takes the iron ore by rail to Saldanha Bay, and it's then exported to the Chinese to import hammers back into South Africa. So the rail is 860 kilometers long. It's got 3 bends in it, so it's basically three long straight strips, and there's a vertical height of 1,300 meters.
Okay.
So my opinion is that there is energy to be gained because the iron ore goes downhill and the empty train goes uphill.
What's the problem, though? I mean, is there actually a problem, though?
The trains need to apply brakes all the time on the downhill.
Okay, so it's wasted energy.
Yes, there's wasted energy.
Okay.
So I think you could either collect that energy and put it into the grid
You're
for other
jumping
trains. I'm jumping ahead,
Yeah.
but I'm trying to work out if there's a problem with solving.
Okay.
Well, I mean, ideally, if you can get enough energy to send the train back up for free, that would be first prize.
Yes.
So is that your task? What's your task? What's your design supposed to be?
I'm not sure what should it be.
No.
Okay. About the train, I would say I don't know, but I'll go and find out about the train.
That's the way that works.
Well, I learnt about trains. Each train has got 342 wagons, and each wagon has 100 tons of iron ore in it.
So we're looking at
342,000.
No,
34,200.
34,000 tons
I
of
made an
iron
incorrect
ore
assumption.
plus the train.
what is this? Okay, I mean, in the grand spectrum of trains and cargo trains, how is that then lined up?
These trains are among the longest. They're 4 kilometers long, and in 1989 they did set a record for most payload.
Okay, so it's an unusual design. It's not this by the book.
So it's 100 tons of payload. What's the weight of each carriage?
I'll
Because
just
if
have
payload's a
to Google
significant
that.
percentage of the carriage, then there's a serious amount of energy to be
So
gained
the
going down.
total train weighs 41,000 tons, and the payload is 34,000
So it's
tons.
a very 75% roughly of the total weight is payload.
Yes.
So you're coming back 75% lighter, or
Basically.
there and thereabouts.
Yes.
Okay, so yeah, no, okay, fair enough. The problem still sounds like it's holding up.
Okay, so then I went and had a look at the sort of brakes which are used on trains, because obviously if they're used, you need to, I think you have to understand how they work.
Sure.
There are hand brakes.
Yes, I tend to stop 342 tons with a handbrake. Very easily done.
There are rail brakes.
Shouldn't be so condescending to the students, Mr. Schekman.
Okay.
There are electro-pneumatic brakes
I wonder which one the student's going to go for.
and pure electric brakes.
Are these all found on a single train, or are there different methods on
This is
all
over
trains?
train revolution,
Okay.
and it's sort of also linked to the design of bogies. Bogies are a set of wheels, left and right. They can be either, as you see on the back of a bus, 4 wheels or 2-wheel bogie.
Okay.
I also investigated how you can take energy from a train and what you can use it for. So there's obviously direct collection, where you put it straight back into the source as you go along.
What would the drawback of that be?
It's unpredictable. It's not immediately available for use back to you, because you're dumping it, so it's not going to be used for the same train. So it would be useful for others, for other things.
What currently powers these trains? I assume they're electric trains.
Electric.
Okay, so they are electric. In terms of their current state with batteries and things like that, are they hooked up to an overhead line, the rail line, or do they have batteries?
The trains themselves are just straight electric. I don't think they've got batteries.
Okay, no batteries. Okay. So, obviously, inclusion of batteries is probably going to increase weight.
Yes.
Okay.
Not if you assume that the weight of the battery is negligible.
That might be what we call a bad assumption.
So the next part of my project, I think I'd like to just show you my PRS, if that's okay.
Okay. Sure. I mean, yeah. Why not? Let's have a
Because
look.
I've read the course outline, I've read ELO 1, and I'm sure I've got a problem that's worth solving.
I mean, technically, I think there's something here. Yeah.
So obviously, it's got to be retrofittable.
But
the current.
have you understood the task properly?
Yeah. What? Okay.
Or
Yeah. Let's take a step
defining
back.
requirements and
Before we-
constraints and
yeah. Well,
criteria?
what was your task here? If you were to maybe summarize it in a sentence or two.
Because you've told us about trains, you've told us about more weight going down than going up, and you've told us about how the trains break. How are we going to take this energy that is being lost or used going down to actually do something? What are we doing with the wasted energy?
Or are you designing an entirely new train? Are
Yeah.
you modifying or are you designing new?
If you're jumping into concepts,
Well, it would. I mean, if you're planning and considering that in
And you
your
also said the
concepts,
D word.
so the problem here is that as I understand it, energy is being wasted.
Okay.
What to do with it? Do you use it for the same train? Do you benefit the communities along the rail line?
But that's the point here. Is your specific design task here the better utilize the energy globally? In which case you can go a whole number of routes here for us.
Yes.
Or are you going specifically for this train retrofitted to save and store that energy?
Well, this is where I would separate and put my 1 foot out of this. Having read this report last night, there's no mention of what the energy could be used for apart from focusing on the empty train going back to collect iron ore.
Okay.
Well, I mean, that is a valid avenue of exploration. I mean, at some point with diving into concepts, you have to narrow it down. Before you even get to your PRS, you have to have something a little bit more specific, because giving electricity to a neighboring village is a very high-level concept. Putting foot warmers on the train is another kind of concept, but you need to just, without defining a concept, focus down on something. Otherwise, you end up in a circular loop of death of what is a concept, what is the problem.
In terms of helping the problem along, there's 1 train per day.
Okay.
So in terms of collecting it for, and there are like almost 0 communities.
Okay.
The only thing which you could do is, in terms of if the actual mine itself or the harbour at the far end was short of power, the power that is collected as you go down could be used at the endpoints.
At the endpoint, yeah.
Or sent back to the start point. Those are all kept on the train. I think those would be the three super high level problems that.
Yeah.
Okay.
And that's what you would pull out of your literature review going into your task as understood. And once you've understood that, you can then actually draw up requirements, constraints, and criteria for the actual problem you're trying to solve.
Okay. So then you have your PRS now, which you've very diligently written up for us. Okay, other than the fact it's not quantified, so incorporate a control mechanism is possibly one of the more arbitrary statements you could ever make.
Yeah, what kind of control mechanism? What are you controlling? Are you controlling the train? Are you controlling the power generation? Are you controlling the storage of the power?
Yes, but what I did is I read ELO 5, and it seems like Mechatronics 2 is the best fit for that, so that's why I added control, because I think there must be control.
So yes, control is important. If you feel that control needs to be one of the requirements and it's going to be a focus of the report, you need more information about what you're controlling earlier on in the report in terms of some literature, and that would filter into your task as understood so that you can then actually pull out a useful requirement from that. So your requirement will have some more kind of specification to it as opposed to just have a control system. A control system can be a man opening and closing a door. It's a control system, but it's not necessarily relevant to what we're doing.
Not to mention, your design might need that control system, but you need to do a hell of a lot of design up front before you can even get close to that. So what would worry me is that you're going to rush ahead, tell me, oh, there's a train somewhere, there's a generator somewhere, there's a regenerative braking system somewhere, but let me tell you about this control system. When you haven't substantiated anything up front, and the nature of that control system, a person opening and closing a door or an artificial intelligence housed in the mainframe, those are 2 different things that have no basis currently. So, and half of that then comes down to the fact that there is no quantification or absolution about that point. It is vague and arbitrary. You're putting down points to try and have points.
So the problem with this report up into the PRS is that there isn't actually any analysis of trains. There's a lot about the sort of design of bits and pieces of them, but there's actually nothing about the mine itself or the endpoint or anything else.
Operating environment.
So that's right. All of that analysis comes after concepts.
That is very self-aware of you, Mr. Student. You'd think having noticed it.
Yes, but I'm repeating, so.
No.
So I've picked up here that you have a constraint which at face value looks like a valid constraint, where you have a maximum braking speed of 90 kilometers an hour. So that could be a valid constraint, but where does that number of 90 kilometers an hour come from? What is the limitation?
90 k's an hour would probably be the 3 bends, and there is a tunnel.
Okay.
But on the straight sections, I mean, really heavy train, it's iron ore. There's no rush.
Yeah. And is that to do with the limitations of the brakes, depending on what braking system is used?
I guess it would be the brakes, yeah.
Okay. So, provided that all of that is mentioned beforehand, that would then be a valid constraint.
Stop kicking the table. Can I go through some of the concepts?
So I assume this would be a later meeting you now have with us.
Yes, I'd have to go and fix
go fix
a heck
that
of a lot of stuff.
And then
Meeting 2.
Meeting 2.
You're late.
All right. So what I did is I read about the 3 concept idea, and I thought I'm going to impress my supervisors, so I came up with 5. Obviously, the first one is the obvious one, which is direct regeneration, where you collect energy at the wheels, you use the same motors that you use to drive it, and you basically pump electricity backwards into the grid.
Okay.
The second one is a hybrid system, where you use a mechanical setup, where you end up with a traction motor and some rectifiers, and you can either put straight back into the main line, or you can have onboard storage.
Okay.
Because the train track is not all downhill. There are flat bits, etc.
Okay,
So
okay.
you could where you need to brake, you can put the energy into the grid. If you need to store it up so you don't need to suck from the grid so much, you can then have onboard storage.
Are you assuming that the grid is able to store the power that you're putting back in for use at other times?
Well, the advice that I would normally give to a fourth year there is, are you redesigning the national grid to absorb different trains, or are you focusing on the train? And for this one, it's a case of there's no mention of that. And obviously, this was a project done from a couple of years ago, and that was before SA had wind turbine farms and things like that. So I don't think at the time it would have been possible.
All right.
But
Okay.
now it obviously would be. The next one would be the good old mechanical flywheel, which is direct energy collection. It requires clutches, gearboxes, etc. Then there's a pretty innovative one, which I've come up. Well, sorry, the student came up with, which is an eddy current rotary collection system.
Take me through that one, please.
Unfortunately, my CAD is so good that I can't really figure out how it is. But anyway, there's some coils. And anyway, ELAN 2000 was my least favorite course. Anyway, there's a hydraulic cylinder, there's a valve, there's a mounting, quite nice drawing. There's a coil, there's a composite casing, a permanent magnet. Okay, there are about 5 spelling mistakes in this drawing. But you'd have one of these on each wheel. Don't worry, it lost. It wasn't a good concept. And then the last one was to hang fans out the side of the train and then collect energy using these wind turbines that stick out the side of the train.
Okay, well, I mean, look, besides the thing that your concepts are basically all over the place, some of them are looking at the kind of energy you extract, some of them looking at what you do with the energy once you've extracted them, and some of them are basically the same thing. I mean, mechanical flywheel is just, you're storing the energy. So the hybrid and the flywheel are fundamentally both storing energy.
Well, and some of these, if you look at the concepts, I mean, the reason that they're like this is because the PRS is not specific.
Yeah.
An actual problem is not clearly defined, therefore your concepts do end up being all over the place.
I would say that in actual fact, your hybrid system is a higher level concept than other concepts.
Yeah.
Because your methods of extracting the energy, you could use any of those energy extraction concepts within your hybrid system in order to create, or in order to extract your energy and then either send it to the grid or keep it on the train. So you are kind of going like high level, mid level in one go instead of first deciding on, is it staying on the train or is it being sent off grid, or are we doing both? Once you've decided that, you can then start to think of, okay, how am I extracting the power? How am I storing the power if necessary? And you can go down the hierarchy like that. But you very much are confusing your levels at this point, and you should never have a situation where one concept could form a lower level part of another concept.
Yeah.
Then you've made a fundamental mistake in terms of what your concepts are.
And if you are a student working on a project and you're sort of worried about how do I identify whether I've got exactly what Dean said, the concept diagrams, if they end up looking like a system diagram where things come in here and they could go over there, so for example, you're designing a racing car and you've got this thing called downforce, Well, there are a million ways to do it.
Yeah.
Yeah, but downforce is part of the problem.
Yeah.
And if you need downforce, that's your highest level.
Yeah.
What you come up with is, so you wouldn't have downforce as concept one and then have different methods of producing downforce in the same set of concepts.
Exactly, yeah.
All right. Anyway, the hybrid system one, I did one of those fantastic weighted tables.
Good. What kind of score did it get out of curiosity, as opposed to every other concept?
Well, my weighting criteria was actually, these things are always interesting. Okay, I've thrown in some cool maths here. The hybrid got a score of 4.79.
Okay.
The next best one was 4.58. I didn't even put the aerodynamic one on.
The criteria you used in your magical table, are they the same criteria that you've listed in your PRS?
Yeah, the standard stuff: production cost minimized, maintenance minimum, safe, efficiency maximized, readily available off-the-shelf parts, the usual.
Those scores are out of 5, I assume.
It doesn't say.
Okay, well, let's assume they are. 'Cause, I mean,
But Mr. Schekman, is that a sound assumption?
I'm worried about it. But my curious point is that those scores are within 4% of one another. So how confident are you that you have a 4% accuracy?
No, but it won.
Yeah.
Like it's the
They got
table
a higher
says
score,
so.
certainly, but the other one also got really good.
In fact, with my weighting, the hybrid didn't actually win on lifespan, but it dominated in part availability, efficiency. It lost out on maintenance. It lost out on production costs.
What did everything else get for part availability? Because that would be the one that
part availability, mainline feed was 7, flywheel 7, and the rotary components was 4.
Yeah. There's no such thing as a wind turbine. They're new technology that doesn't exist.
All right, so obviously I'm now getting into the last 2 weeks of my project, so I'm not gonna see you until I'm gonna send you the draft the day beforehand. So I'm just gonna discuss my analysis. I'm gonna try and work out how much energy the train has.
You mean when it's...
Yeah, so I've got a route profile.
Cool.
So I can work out, I know the mass of the train, I've got the rolling friction.
Change in height.
Yes, because I've got the route profile and I've discretized the route into the steep bits, the flat bits, etc. So I can work out all the energy.
Okay.
And then once I've got that energy, I can then work out how much is immediately storable for onboard use versus putting back into the main line.
I mean, yeah, sure.
And then for my detailed design, can I just do some CAD drawings of the assembly that holds this thing to be retrofitted onto the train? Would that be okay?
What is the analysis, though, as part of that?
I'd do some stress calcs and FEA.
If you did them properly and you're able to substantiate that, your stress calcs, you're probably dealing with a high load, a lot of acceleration and deceleration, I think that there could be something there.
So it needs a gearbox. So if I design the gearbox.
So what needs the gearbox exactly here?
Collection from the wheels.
Okay, so if you do, so your gearbox analysis is going to constitute.
Yes, because the electric generator has to run at a certain speed for efficiency,
okay.
And the train runs at a variable speed.
Okay, so you're certainly getting quite a few elements to your design here.
To your what?
Okay. Can't suddenly just start using them. Okay, sure. I've lost what I'm going to say now.
That's what happens when you use banned words.
Okay, but my point is, you're going to do a gearbox design. Let's assume a gearbox is necessary. I'm sure you substantiated that. The nod is appreciated. Thank you for audio listeners. And the design, so if you then do your stress analysis, you've determined your gear ratios, I assume.
Yes, and I determined the gear diameters to 8 decimal places for accuracy.
I wouldn't say you need to put that in the report, but sure, okay, you at least know you're
And then I've sort of written an operating manual on how it all works, like a system flowchart. I think a wiring diagram would be quite good.
I don't know if that's necessary, but sure, okay. Well, and then technically, if you've looked at the entire loads, you know your energy, coming into your gearbox. I'm going to say, I assume you know this because it's easier for me to ask otherwise. You know your energy coming in, therefore you know what kind of loads need to come through that gearbox, what kind of speeds are coming through that gearbox, you know the speed of the train, I hope, and yes, you should therefore be able to calculate a really nice gearbox, analyze that, stresses and all that good stuff. Yeah, I think it's a good fourth year project.
Cool. All right, so can I send you the report just before I hand in, if I have time.
Yeah. Okay. I mean, yes. If there's anything I think you have time to change, I'll let you know.
Okay.
Dean, is there anything that you think needs to be in?
Answer.
Yeah.
Just when you are writing up, make sure that you focus on things in order of importance. Don't show me a 7-page wiring diagram and give me 3 lines on your gearbox. So make sure the big, more important things come first and you get all those done. And if the little things get left out because you run out of time, it's fine. But make sure you get it all the important stuff in.
And that glossy look in your eyes means I don't think you've heard me, because I think I'm not going to see that. Or I am going to see what exactly I've told you not to give me.
Okay, so we started off by talking about good assumptions and bad assumptions.
Yeah.
Okay, now there's a difference between a bad assumption and an outright mistake.
Sure.
And I think that is going to be explained now. So to do the energy analysis, the critical gradient on this course was negative 0.84%. So that's the gradient.
Okay.
And then there's an equation here, which is the main assumption, where the drag force of the train is equal to the weight of the train.
So first of all, it's completely incorrect, but is there any attempt at explaining why that was the assumption?
Yes, I'm now going into the analysis of what I did after that assumption. So,
Whoa. Okay. So you can use that value. I'm still interested. Do you understand?
No. You've done your job of supervision. I've done this. Right. So,
okay.
So what I did is I plotted drag force of the wagon, which is equal to its weight, and then I plotted using.
So you plotted a straight line.
That's the mass of the train. It's constant with speed until you get to the speed of light.
So is the drag also constant there?
No, the drag is it follows the v squared term, and where they intersect is my design point.
Why?
Because the point of intersection of the two curves satisfies the energy balance. I can't figure this out, but it's written here. What that does is it gives me a speed of the train of 2,578 meters per second. That is at the end of the track.
So just in case everyone listening explicitly trusts everything that Michael says,
I think that's
this
8
is
times
all
the
wrong.
speed of sound.
No. If you're getting these answers, these should be the warning bells. These are where I've made a bad assumption here. In fact, no, that's not even a bad assumption. That's not an assumption.
It's an error.
That is a critical misunderstanding of physics. ELO 2, bye-bye.
This is grade 8 or grade 7 physics. So what I do is I've now got my velocity.
It's Mach 8.
I can work out that the rotational speed of the wheels is almost 3,000 radians per second. Wait for it. I can then calculate the power, because power is force times velocity, right? Now the force is the weight of the train, multiplied by 8 times the speed of sound, but I'm going to divide that by the number of axles to work out the power per axle.
Good, I'm glad you did.
And I get 200 megawatts per axle.
Doopy,
This whole train has got 3 times the total installed capacity of Eskom. Let alone if it went off Saldanha Harbour with a slight upward ramp, it would probably get to New Zealand in.
So load shedding problems have been solved. We just need an eighth of one of these trains going down to Saldanha once a day, and we are sorted. You are going to be a very, very rich person.
So I then calculated the torque, which was in kilonewtons, wrong unit. I then knew that I had to design the generator to spin at 6,000 RPM. So I worked out the gear ratio, which is 10.5. I then worked out an axle gear diameter. But I then needed to work out how many motors I need for this. So, of course, what I did is I took the amount of power per axle, which is 200 megawatts, and I divided that by the power of the motor, which I found off the shelf. And for each axle, I need 10,030 electric motors to collect the power. I'm just going to read the paragraph.
So 10,030 motors per axle.
Yeah, I'm just going to read the next paragraph.
How big are these motors roughly, just to put everything into context?
That's not in the report. But the next paragraph is helpful. The required number of motors is too large. Thus, due to space considerations, only 4 motors were assumed instead, and the maximum recoverable energy was approximated to be less than 80 kilowatts at this point, and
No.
then the design
Okay, so
follows.
you've figured out at this point that there's something dodgy going on with your numbers.
I don't know what it is,
And
except
instead
that
of trying
10,000
to
motors won't
Go
fit.
back and fix it, you're just saying, cool, that number's too big, let's just use this number instead.
And not even like a round down. That's 1,000 to 4.
It's
That's
almost
10,000 down to 4.
That's-
10,000 down to 4.
Yep.
But I had to keep costs down as well. I mean, and none of this is what the student justified, but this is, at this stage, you get to the report, and if you're kind of dozy when you're marking it, you might not look at the number because, well, this is
Sure.
the 5th report you're marking.
Yeah.
You're going to get to something like that where you just see 10,000, what the hell is
Yeah,
going on?
sidestepping
You
a little
start
bit.
paging back, and you then go back to the beginning. And at that stage, you become, you're really looking for...
Well, I mean, a big part of these projects isn't only can I do the maths, can I do a calculation and get a number out. It's can I actually spec out a system that is somewhat reasonable. It doesn't have to be something that is guaranteed to work, but it has to be
Yeah.
within the realms of possibility. This is clearly outside of the realms of possibility, but there's a whole lot of maths to back it up. I would argue that a final design that might work with no calculation to back it up is more viable than something with a whole lot of calculations that are all meaningless.
Well, technically, if you actually stripped every calculation from this, and I told you this design has 4 motors,
Yeah.
it's traveling down at the speed it will go. Let's not specify speed because that will throw warning bells. So let's just tell you it's 4 motors,
It
regenerative
goes
braking.
down at train speed.
Go down at train speed. It's the new unit we use now, and it then has a gearbox, and this is the size of the gearbox. I'd say, hell, even looking at that spec, I'd say, yeah.
No, I mean,
But at the same time, though, if you don't have calculations, though,
yeah.
that's means there's nothing to back up anything.
Yes, no,
with that, so,
exactly.
And I think, the advice that I've got for students is, when you go and you meet with the supervisor, don't just go there with your plan, what you're trying to do. But don't just go in there with detailed spreadsheets and graphs and a whole lot of sort of noise. The fact that you're doing the calculations mean that you should be understanding what you're doing.
Yeah.
A couple of the highlights and a couple of the decision points. And those decision points are actually your assumptions.
Yes.
And I think that's how you need to sort of, as Dean said earlier, prioritize the assumptions. And just check that your assumptions are okay.
Yeah.
Yeah, I've assumed weight equals drag. Excuse me, stop for 1 second
Why?
there. I can't even visualize how that works, how you keep weight equal to drag for a train.
As you go faster, you pick up more weight.
Just picking up the cows on the side, just scooping them up at Mach 8.
Or you make sure that you just control your speed so that your weight is always equal to drag, and you'll get a slight change because acceleration due to gravity changes as you go down.
I mean, that needs a control algorithm.
Well, he wants a control system.
Sure. Yeah, okay, so, I mean, we might have to cut this, but did that student pass?
No.
Okay, thank God. Okay. I mean, I'd never going on a train again if I found out that student had. Sure. Okay. So yeah, so there's very much a difference then between or a bad assumption and just misunderstanding physics. Saying weight equals drag is not an excuse to make your life easier. Like, if I assume this, that makes my calculations so much easier, so I'm just going to assume that.
But also so much more wrong.
Well, I mean, let's ignore that side of things because it seems many times that is the basis behind it. I want life easy, I will assume this. A bad assumption is, okay, physics is still working, but I'm going to say physics is... We assume constant air density is an assumption.
For an airplane.
I mean, even for a train, look, it's going Mach 8.
Yeah. If it was going at 30 k's an hour, you wouldn't need to worry necessarily too much about air density in an electrical
As
regenerative
long as you
system.
include compressibility.
Yes. And the melting effect and your ablative armor you need at the front of the thing because...
Look, you start off with
Ceramic
iron
tiles.
ore in South Africa. By the time you rocking over South America, it's turned into nails and...
It's the transportation and furnace all in one.
And a butchery for anything that happens to be
you get to the
in the
harbour and
vicinity.
you just pour the molten iron into the molds and you ship the finished products out. I mean,
And a demolition device, because the moment they hit Saldana Bay, it's leveled Saldana.
So I guess it's safe to say that this project was derailed by a poor assumption.
I know what the rule is going to be for next week. All right. I mean, we've well gone over our 20-minute time limit here. I think that's a good length. We'll look into splitting it, otherwise we're just going to keep it as one big long one. So if you want shorter ones,
we'll try.
We'll try, but we like to talk. It's part and parcel with why we got the jobs we did.
I think we're just calibrated on a lecture's 45 minutes, so
I mean,
everything we do takes 45 minutes.
Kind of dead on.
40,
So
45.
Yeah. 40,
40,
45.
45. All right, then I think that's good enough. Thank you very much. The other questions are, when doing detailed design, how do we as students know when to stop?
5 minutes before hand-in.